Hello everyone from Finland, from University of Jyväskylä, but if you put it to Google, it will be Jyväskylä, so don't get lost. It is my big pleasure to present today the first of our papers titled Cybersecurity of COSPAS-SARSAT and EPIRB, the threat and attacker models, exploits and future research, co-authored with Syed Kanter, Hanno Turtiainen, and Timo Hämäläinen. This is the agenda that I try to propose for today's talk. We look a little bit at on the background of what COSPAS-SARSAT, EPIRB means. We try to define a little bit the problem statement, but we try to address with our paper and research in particular. We will also try to emphasize a little bit the related work, but closely is related to the work we have done here. Then we detail a little bit the methodology that we used to run our experiments and how we implemented that. Then we shortly discuss the results and challenges that we faced during the experiments. And we try to outline future works, direction, solutions, and summarize our main contributions from the paper. So a little bit of background. So COSPAS-SARSAT is an international program for search and rescue, or SAR in short, missions that are based on satellite-aided tracking system, or SARSAT. It is available, the specification and the documentation are available at this URL. And the first part of the definition, the COSPAS, actually comes from, I think, Soviet Union time, which means Космическая система поиска аварийных судов, means basically a search for vessels and ships in distress. The COSPAS-SARSAT is a very critical system in the sense that it is the core backbone of the global search and rescue system. So basically all the major missions, rescue missions or distress signal missions happening in open waters or in hard to reach or observe areas, they usually are being supported by COSPAS-SARS system one way or another. Of course, it is not a fully global system, maybe like GNSS, GPS, Galileo. It is composed of 45 national agencies in all nations, and of course, the COSPAS-SARSAT cooperates actively with International Maritime Organization, well, because of the vessels and the protocols they support for vessel rescue. International Civil Aviation Organization, ICAO, of course, for aircrafts that have gone missing or are in hard to reach areas and also send distress signals. International Telecommunication Unit for obvious reasons. So this is a very nice slide, courtesy of International COSPAS-SARSAT program, which is kindly provided with really nice licensing terms. So I try to quickly explain what happens in COSPAS-SARS system to give you a background. Normally, when there is a distress, for example, by a person who is lost in the mountain or in the woods, or for a ship like a cruise vessel or other type of ship carrier having a distress in the sea, or aircraft crash or malfunction, and similarly to bigger aircraft, more commercial aircraft in open waters systems. So they send or they use a particular type of device that sends the COSPAS-SARSAT signal on 406 megahertz band to LEO or GEO types of satellites. And there are a couple of systems or protocols or types of devices that are being used. In particular, there are, for example, PLB, which is personal locating beacon. It is usually used by persons or individual rescuers in fires or avalanche missions and so on. There's the ELT, emergency location tracker for smaller aircrafts or general type of aircrafts. There's emergency position indicator radio beacon, which is predominantly used on big commercial vessels and so on. So they send these signals of 406 megahertz, which we will see that it's not highly secured, so to speak. There is no encryption, but encryption is not a problem. I think integrity is one of the main concerns with these satellite-based systems, ADS-B included. Then all these signals were passed to the LUTs, or basically local user terminal or ground mission station or ground stations. As we've seen in Keynote, there are different ground stations that process different types of signals. So they receive all these types of COSPAS-SARSAT. Then the data is being processed and is sent to eventually a different processing center, which is mission control system. Another set of people look at these signals, they triage them, or they try to make a decision making based on the protocols, and they send it to RCC, which is a totally different system, which is rescue command center, and then they send the search and rescue crew with the positioning of that data. There are about 8 different types of positioning data, and there are about 5 different types of protocol data inside the same data stream. So the problem statement for us was to try to see how secure or insecure are the COSPAS-SARSAT protocols. Another research question we try to ask in this work is how easy or feasible is for a potential attacker is to attack COSPAS-SARSAT protocols, devices, system processes. For example, we see there is a very complex chain of events that happens and what could be the consequences. Then what types of attacks can be implemented in the lab, for example, and are successful, evaluation of those attacks, and eventually to try to propose directions for how COSPAS-SARSAT can be secured in the future or short and long terms. So the closest related work, well, it relates a little bit to other avionics and aerospace systems like ADS-B that are used by aviation, but also for satellite-based ADS-B. We have also the work from Martin Strockmeyer and their group on ADS-B as well related. And we have a couple of other recent works that we've published where we actually look at the fuzzing and software implication of exploitation of such protocols. For example, finding stack-based overflows, crashes that can be abused to further escalate or to do let's say, exploit and malware injection into a compromised satellite, into a compromised device, or a ground station, and so on. Basically, all the elements in this highly complex chain system. The methodology we try to apply to this work is we use the generalized form of but we proposed in Ghost in the Air traffic, the ADS-B type of attack we proposed in 2012. Essentially, it is, I think, even that work is a redo of similar approach, where we identify the possibly insecure aerospace, maritime, or any other protocol for that reason and get their spec, whether they're open source or acquire the spec if it's pay for play. Then, of course, read the spec, implement the spec, essentially doing the coding and decoding implemented. In our case, we use Python and radio type of implementations. Of course, we also usually need to do modulation and demodulation because we try to use software-defined radios, and that is our software-defined front end. And for that, we need additional effort again. Then using the cross-testing like modem, modulation, demodulation, and codec, coding, decoding, that they work in closed circuit for our implementation, meaning that we basically validate that our implementation at modulation and coding are okay. And then essentially we go in a loop where we generate input and output for packet protocol packets that we subject to the devices that we own. In particular, we acquire a certain set of devices that are real-world devices, and in the second talk, towards the end of this workshop, I'll show the lab and the devices we have actually used and built on top. So we subject these devices and the software that run on those devices, or the software that runs on a normal computer, processing this type of packets, then monitor the system, whether it crashes, try to collect as much log as possible, or any crash dumps, and any forensic type of information that can help understand the nature of the crash or the problem, and then try to improve the attack. So essentially, anyone who has done protocol fuzzing or protocol vulnerability research and exploit discovery, this is essentially quite common steps to approach this task. So we used multiple SDRs successfully in our COSPAS-SARSAT tests. We have a couple HackRF devices, we have a couple of BladeRF devices, different hardware revisions of them, different models. We also have Pluto SDR, so we just want to make sure that our systems and packets and modulation and codecs work cross SDR devices, so it's not tailored to a particular device. We also use a McMurdo G8 AIS transmitter, which is a commercially available device that has all the functionality of a certified EPIRB COSPAS-SARSAT device. And it also has an AIS. Basically, it's also a maritime beacon as well. So it transmits at both 406 megahertz and also 121 megahertz, which is AIS, one of the AIS frequencies. These devices also come very conveniently with a test function that generate certified low power signals with their identification number, and you can capture that signal for, let's say, investigating or replay or things like that. So they are very, very convenient and very good investment for a lab. We implement all our stuff in GNU Radio, GRC, and Python-based scripts, so we can automate the entire testing and fuzzing process. One of the limitations of our experiment, and this is somehow inherently related to what James mentioned, that space is such a critical system that not everything is accessible, even though you have all the desire and all the attacks possible. Some software or some devices you will never get. So software for COSPAS-SARSAT apparently is available in ground stations, mission control centers, and rescue centers. And we don't have access to that as of now, but there's fortunately EPIRB plotter, which is not open source, but it's software available for a small fee, which decodes EPIRB beacons. And there are essentially two types of beacons that it can decode, the short and long ones. And they, as I mentioned, they encode about 8 different position protocols and about 6 different types of packets. So the threat model we've tried to look at are the basic replay, the spoofing, where there are several types of spoofing that we propose in our paper. The basic spoofing that everybody knows, just to change some identification or positioning data. And then some theoretically discussed the close to target mimicry spoofing that is basically, for example, a drone-based system that flies close to the target aircraft or to the target ship and spoofs the data to something very similar, but yet maliciously modified. Whereas the overwhelm spoofing is more like a denial of service or link resource exhaustion attack. And then there's the overwhelming plus close to target mimicry spoofing. And this is essentially equivalent to operational equivalent of distributed denial of service amplification attack, where, for example, every spoofed and overwhelming spoofing attack generates a lot of decisions and chain of events in the entire ground station, MCC and RCC and SAR crew, and basically it puts the whole system to a halt. And then we also tested the network application fuzzing and exploitation. So the ones that are bold and underlined are the attacks that we've tested. We have the main results that the replay and spoofing works flawlessly. Essentially, we've been able to spoof and replay the EPIRB MMSI, which is basically ship-related or AIS-related protocols, the EPIRB ELT, the emergency location transmitter for aircrafts, and then the serial location protocol, which is basically the PLB-related one. We've also performed fuzzing, but unfortunately, so far, we haven't been able to create the system, the EPIRB plotter. However, it comes from the same vendor, which does the ship plotter, which is the AIS equivalent, which we have previously been able to crash with potential remote code execution. Or
right. Could you wrap it up?
Yes. So the challenge is that the system is highly sensitive technology, so it poses high risk, so research is limited. And also the access to the system and software and the access to the stakeholder is also not easy. So the research is limited in this way. Future work and solutions that there is a need for message authenticity, lightweight PKI and digital signature. There is a need for message freshness for anti-replay, and need for randomized and confidential IDs in order to avoid spoofing sensitive targets. And basically, I will say thank you, and I'm open to questions or comments or any discussion. And please contact me at this email address. Thank you so much.
Yeah, very interesting talk. Thanks a lot. For your future research, have you considered also looking at the physical layer, because there is ongoing R&D work in the SAR community to define a second generation waveform, which could be, for example, a wider band spread spectrum waveform, where then interesting security properties pop up with either random codes or crypto codes and things like this. So if you Google for SAR search and rescue and spread spectrum, you can see some of the work that's ongoing, because the current waveform is a very narrow band channel, which brings a lot of the limitations.
Yes, so that's a good question. We have that's basically the first attempt at looking at SARSAT protocols. Normally, of course, there are low-hanging fruits, and this protocol, as is right now, is one of those cases. And our idea is that it's better to know the low-hanging fruits faster rather than later, and try to address the problem as soon as possible before the bad actors do. I think your comment is timely, and definitely that's something to look at, the spread spectrum techniques for these protocols, not for SAR, but all the related protocol could be applicable. I'm not quite sure how fast they can be implemented. For example, for ADS-B, we know these problems for more than a decade already, but still the investment done so far and the impossibility to upgrade everything. And there's also a lot of resistance to upgrade because of the investment done. So there's also, let's say, less than technical reasons that this system stay insecure. And I'm afraid that this SARSAT system is in similar position, but I hope I'm wrong. And thanks for the suggestion.
From my side, I mean, you did a lot of research in aviation, aerospace. Is it the same? Do you have other challenges? It looks like you use the same generalized frameworks that you use on aviation, on maritime. But yeah, do you encounter anything different or new, or can we just use the same methods?
Well, I think the methods are essentially the same. We don't, in my opinion and in our experience, we've applied the same methodology for ADS-B, ACARS, AIS, now EPIRB, COSPAS-SARSAT, and I think we can certainly map it to CCSDS that was mentioned in the keynote comment. And I think the methodologies and the techniques are essentially the same, with maybe small tweaks here and there. And the type of exploits that are possible on the devices, on the systems, and on the software are essentially the same as we know them for Windows, Linux, Mac OS, and embedded devices in IoT. So I would, essentially, I will not be surprised if tomorrow somebody does a remote code execution on a satellite system, because essentially all these problems are known. It's just that security by obscurity prevails, or lack of awareness prevails, and these problems are coming to light, let's say, too late. But we all know the methods, and we kind of already know the results. And I think if we take any other low-hanging fruit protocol, it will be prone to the similar problems, applying the same methodology but we did here. So I hope that answers your question.
Yeah, that's. Thank you.